This genuine Unreal Engine 5.5 run starts with a 12-point rope hanging from a red anchor. The anchor moves sideways, the rope bends and swings, a purple tip trail records the motion, and damping lets it settle while every link stays close to its target length. In this lesson, we will store current and previous point positions, reconstruct velocity without a separate velocity array, apply gravity with Verlet integration, pin the first point, solve 11 distance constraints 10 times per step, render the nodes and links with instanced meshes, and protect the result with automation plus 4 native Unreal captures. The simulation owns 2 matching arrays, positions and previous. At initialization, both arrays contain the same 12 points, spaced 62 Unreal units apart. Equal values mean 0 reconstructed velocity. For point I, current position minus previous position is the displacement carried from the last step. Multiplying that displacement by damping removes a small amount of energy. This compact state is the main reason Verlet integration is approachable for an AI-assisted C++ lesson. The data, update rule, and invariants are explicit. For every point except the anchor, copy current before changing anything. Reconstruct velocity as position minus previous, multiplied by 0.965 damping. Then calculate the next position as current plus velocity plus gravity times delta time squared. Finally, store the old current value in previous. The runtime limits a simulation step to 1/30th of a second, while the automation test uses 1/60th. A production rope often uses a fixed accumulator and several substeps, especially when frame time varies or collision is added. Point 0 is not integrated like the rest of the rope. Before integration, before every constraint pass, and after the final pass, both its current and previous positions are set to the anchor. That removes inherited velocity from the pinned point and prevents iterative corrections from moving it. In the demonstration, the anchor waits for 1 second, then moves from -280 to +280 on X with smooth step over 0.7 seconds. That controlled input creates the driven state and gives us a repeatable regression signal. For adjacent points, delta is point I plus 1 minus point I. Its length is the current link distance. Dividing distance minus rest length by distance gives a scale for the correction vector. The first link has a pinned endpoint, so its free point receives the whole correction. Every later link splits the correction evenly. The first point moves forward by half, and the second moves backward by half. One pass improves the rope, but corrections on one link disturb its neighbors, so the solver must iterate. This rope performs 10 constraint passes per step. More passes usually make the links appear stiffer and reduce length error, but cost more work. Fewer passes are cheaper and can look elastic. The final runtime reported a maximum current error of only about 0.02 Unreal units. Damping is a separate control. A value near 1 preserves motion, a lower value settles faster. Keep both values exposed, measure constraint error and tip speed, and tune them together instead of relying only on how one recording looks. These are 4 genuine game mode frames from one compiled Unreal execution. Ready shows the vertical rope with no trail. Driven captures the anchor pulling sideways while tip speed rises. Swinging shows the curved rope after release, and settled shows the final hanging shape with a long purple history of the tip motion. The 12 points, 11 links, colored anchor and tip, instance geometry, floor lighting, state labels, constraint error, tip speed, and trail count all come from the included C++ project, not generated stand-ins. The Unreal automation test passed with 1 success and 0 warnings or failures. It simulates the same 12 points, moves the anchor, and verifies visible tip displacement, bounded segment error, low final speed, stable point count, state labeling, rest length, and damping defaults. The off-screen D3-D11 run produced all 4 captures, moved the tip more than 460 units, finished near 0.02 constraint error, recorded more than 100 trail points, completed over 1,800 steps, and reported valid true. Together, these gates test both the algorithm and its presentation. The reusable pattern has 4 parts. Integrate free points from current and previous positions. Pin any kinematic endpoints. Iterate constraints until link error is acceptable. Then render from the solved points, never from stale input data. This demonstration intentionally omits collision, bending constraints, tearing, multiplayer authority, and parallel solving. Add those only after the basic invariants are covered by tests. For AI-assisted Unreal development, this is a strong feature shape. The code is local, the inputs are numeric, the outcome is visible, and regression checks can reject a plausible-looking but incorrect result.